That's all I have.
Yeah.
I don't have words for anything.
So I think that's but thank
Hey.
you for telling me this.
Good afternoon, everyone. So today we're going to do section 9.2. We're also getting a 10.1. Just 10.1 is an introduction to the hypothesis testing. And so we'll be able to cover 9.2 and 10.1. We're taking off where we left before in 9.1. It's still confidence intervals. 9.1 was confidence interval about a population proportion. So we're going to find the confidence interval about a population mean. So it's going to be very similar, except for our point estimate, that thing at the beginning before the plus minus, we won't use p hat, we're going to use x bar. Okay? So I'm going to write a formula on the board. I'll write it out and I'm going to cross things out and show you what the real formula is. I'll explain it. So I'm going to be like, all right, a confidence interval. I'll put my, I'm going to put the point estimate here. This is the math formula for it. The point estimate. I'll put a plus minus and then I'm going to put the margin of error. All right, the margin of error. And this formula is on that sheet that I just passed off to you, but I want you to see this. So the point estimate, we're definitely going to use the sample mean as our point. Boy, if we're trying to estimate a population mean, we're going to use the sample mean as our point. Go out and get a sample mean, right? Sample about 30 cars or 30 people and get an average. Plus minus, now do you remember this? I had to put like a z-score, and this meant how many, like z-score will tell you how many standard deviations above or below the mean you have. So z times this is going to be the number of standard deviations right here. So I'll put SD for standard deviations. So how many standard deviations? And we're talking about the distribution of the sample mean. Okay. So then, what's the formula for the standard deviation of a sample mean? This is coming from section 8.1. This had an S here, and this had the square root of n. Okay. So here it is, but this is not the exact formula that you're going to use. We'll talk about that. I'll explain why. So this should be it. You're like, there's our confidence interval. We got the point estimate, plus minus, z-score times s over the square root of n. The story goes, there's a gentleman, his name is William Gossett. Oh, and this is like 100 years ago. And he worked for Guinness Brewery. Anybody familiar with Guinness Brewery?
The beer?
Guinness Brewery, yep. Still exists, right? Well, his job was making sure that beer tasted, just perfect. The stout of beer and everything. That was really his job. And he did a good job of it. But he actually was really into mathematics, statistics, especially statistics. And he ran numbers and everyone, and he ran into trouble with something. He knew there was a problem. See, he had to deal with small samples. Now, everyone, he was tasting the beer, right? Trying things, mixing, tasting the beer. Does anybody understand why he had to use small samples?
Because
It's not like he had a team of people, me. What was going on?
Your taste goes away the more you drink.
Or something, well, something else. He didn't have like 100 people to taste his beer for him. Who's tasting it?
Oh, just one person.
Yeah, William. So what would happen if he used a large sample size? He'd drink beer all day.
He'll get drunk.
All day long, he'd go what?
Drunk.
Stumbling home and stuff, right?
I want that.
So he had to use these small, little sips, small sample sizes, but he knew something was going on, something was wrong with this. He knew there was a problem, and he found out that when the problem was this, that this right here, he was using, or excuse me, let me put this here. This was here originally, so I apologize. And when this is what we had from section 8.1, so right here I'm going to put, this was section 8.1. This was the standard deviation for a sample mean. What he was doing, everyone, he was using S in place of this. And that was causing trouble for small sample sizes. So, all right, let me get out the yellow chalk. So he replaced this with a what? With an S. All right, great. But then he had trouble, so I'm going to put the sad face. He realized he had a problem, right? Because of small sample sizes, this really wasn't working too well. So he created what's called the t-distribution. So because of this, don't worry, he fixed it. He came up with it. He said, we're not going to use z, we're going to use what's called a t-distribution. So let me rewrite this. I'll put it up there and I'll leave it all class. This is actually what we're going to use when we're trying to estimate a population mean, or do any inferential stats about a population mean. Okay, so let me write this out real quick. And I saw some people had some hands up, and that's good. You had questions, but I'm going to put up real quick. Confidence interval equals an x bar plus or minus not a z-score, but a t-score. I'll talk about that, the t-distribution. I gave everyone copies. And then you're going to multiply the s over the square root of f. So, what were the questions?
S is for the sample and that thing is for the population, right?
Exactly.
See-
So does this make sense to you, Art? Gossett didn't know this. If we're trying to estimate a population mean, we don't know the population standard deviation. Does everyone agree?
Yes.
We don't know that. So he was using a sample standard deviation in place of that. And there's the trouble. Now, it works fine. I'll tell you what, it works fine if you got large sample sizes. Because of law of large numbers. It works fine, everyone. But you get a little trouble, you get a little bias, you get variability when you got really small samples. Well, no problem. He fixed it with this t-distribution. Cool? So anyways, everyone, I do want to highlight one important thing. Would you put this in your notes? Ready? The question is, what is the key criterion why we use a t-distribution rather than a z-distribution when doing inferential stats about population means? And we're going to come up with the answer. And then we'll finish this up. All right, what is the key criterion? Yeah, criterion, and you can just go reason. What's the key reason? What's the most important reason? What's the paramount reason? What is the key criterion for using this letter T, which I have up here right now, rather than, what do we always use?
Z.
Z. And you go, when are we going to be doing this? When we do inferential stats. Inferential statistics. You can just put STATS, period. About inferential statistics. And this is dealing with the population mean. For population means. Okay, someone puts this up, I'll put a question mark, we're going to put the answer. What is the key criteria, the key reason that we're using this T rather than a Z? When we're doing inferential stats, that means doing confidence intervals, but we're going to do more inferential stats. We're making inferences on populations. Inferential statistics for population means, or about population means. And the reason was right there. So let me circle it. What didn't we know? This is called the trouble. This is the reason. This was unknown. That's what caused this whole dilemma. That was the start of the entire trouble for Gossett. He discovered it. Hey, by the way, you know what happened in real life? He wanted to publish this. Well, this is a business, everyone. And you know a lot of business like to keep secrets? Because of competition and stuff? So the Guinness Brewery had a policy. You can't publish anything, you know, that's coming out of this company. He was like, listen, this is not going to make our competitors any better. I want the entire world to know about this. So they're like, okay, listen, we don't want any of our other employees to get upset. Publish it, but publish it under some other name. So not your name, William Gossett. So he published it as under the name student. So it's called the student's t-distribution. That's a true story. So that's what it's called. If you Google this, it's called the student's t-distribution. They wouldn't let him publish it just because of that reason. All right, so we got our happy face. This is going to work, but I'm going to put the answer right here. What's that symbol right there called? This thing.
Standard deviation.
Yeah.
Not sigma, the other one.
And I'll erase all this. This thing, everyone, is called the population. Oh yeah, it is sigma.
Sigma.
But it's the population standard deviation. And the trouble was, you go, what was the key reason? This was unknown. That's the reason. I think it's so important you know that. So that's why I'm going to put it here. Make sure you remember that. It's the main reason why we use T rather than Z. It's what caused the entire dilemma. When we had this, let me write it up again. Remember I had this first? And I had this? Well, what was Gossett using in place of this?
Yes.
He was using, because we didn't know this, look, it was unknown, he used this, it caused trouble, so then we had to replace this with a what?
T.
But what started it? That thing. You go, what is it? The population standard deviation. It's unknown. Now, hey, on a test, if you blank out, would you look at that sheet I just handed out? Somewhere on that sheet it shows that. It goes, this is unknown. This is the reason. This is unknown. Cool. Hey, by the way, I'll remind you of this in future classes. I think it's great you know this. Hey, to keep things simple, everyone, last class, 9.1, we did confidence interval about a population proportion. We use Z, right? Now we're doing confidence interval about a population mean. We're not going to use Z, we're going to use what?
T.
T. So to keep things simple, we're just going to say, whenever I'm doing inferential stats about means, we're going to use T. Now, what's a good way to remember this? I got a way that works for me. I don't know if it's going to work for you. Does anybody know Mr. T?
Yeah.
He was in the Rocky 3 movie. All right, he's really mean looking. Has anyone seen him?
Yeah, 18.
Tough. I mean, if you see Rocky, I mean, tough guy. So I always think mean Mr. T. I hope that helps. Mean Mr. T. So whenever you're doing inferential stats about what? Populations means, you're going to not, don't use Z, use what? Use T. And you go, why? And there's the reason. There's the reason. Cool? By the way, I do want to point out, we'll talk about that T distribution. It's not a big deal if this is a large sample size. So if you got like, if you sampled like 150 people, I'll be honest, it doesn't make a big, huge difference at all if you use Z rather than T. This was really a problem because Gossett was using small sample sizes. So, can we talk about the T distribution real quick?
Yeah.
Then we'll get to a problem. And we got to copy this. I think one needs it next. One row right here. Would you pass this back? There you go. All right, this is the T distribution. The T distribution is like the Z distribution. The T distribution is bell-shaped. Here. Whoop. It's bell-shaped. But it's based off the sample size. Okay? Gossett invented this so that it changes. This changes depending on the sample size. Now, does anybody remember my story about degrees of freedom about 2 months ago? I said if you got 6 donuts or you got 5 degrees of freedom, you know, because the 6th person walked in the door, there was only one donut, and they had no freedom to choose. Do you remember this story? So 6 donuts, 5 degrees of freedom. Well, the formula, because on this sheet you're going to see a DF for degrees of freedom. I'll put this up here. I'll leave it up all class. Degrees of freedom always equals sample size minus 1. DF for degrees of freedom. So just to make sure everyone understands degrees of freedom, it accounts for bias. If you got a sample size of 4, DF is 3. If you got a sample size of 10, DF is 9, right? If you got a sample size of 100, what's DF? 99. Anyone got that?
Yeah.
Because on this sheet, look in that left column, at the top left, does everyone see a DF? So when you look at the number that you want for your T-score, we're all going to look, well, what's the sample size? And then we're going to look at the degrees of freedom. Okay? Cool. And by the way, it doesn't have every number, so we use the closest number we can from the table. It's going to be totally fine. Does that sound cool? And so this changes depending on the sample size. It's bell-shaped. In the middle, guess what T equals?
0.
Just like Z, T equals 0 in the middle. T equals like a 1 here, and a 2 here, and a 3 here, and a -1, -2, you bet. But most importantly, I want you to know that this thing, in this table, the bell actually kind of changes. You know, the shape. It stays bell-shaped, but it keeps changing depending on the what. So I'm going to draw a few bells here. It changes depending on the sample size. And this is my favorite part. As n approaches infinity, the T distribution turns into the Z distribution. Isn't that cool? So look at the very last row of this sheet. Look at the very last row of this sheet, above those percentages. Look at these DFs. It went 80, then it went 100, and then it went 1,000. So does everyone see this? Degrees of freedom. This is the T distribution. 80, then 100, then 1,000. What's the next letter? Z. So what's happening after a sample size of 1,000? You might as well use which distribution? Z distribution. So that's what's key to this whole T distribution. Eventually, you get a sample size big enough, like 1,000, it's turning into the what? The Z distribution, as that approaches infinity.
Gossett made this to account for very, very small what? Sample size to account for the bias because we didn't know that daggone population
So-
deviation.
T distribution is the same as Z distribution, just for small size.
Yep, it's not the same as it, it's the same as when
It becomes
n becomes humongous.
humongous.
But this had to be invented to account for this variability over here, just with means. We don't need this for the population proportions when we're trying to estimate a population proportion. He just knew when this was like a sample size of 10 and a sample size of 30, dealing with putting this in place of this didn't work right.
So like Z equals to like X minus whatever mean divided by standard deviation. What is the formula for T?
Yeah, I love it. Everyone, see, remember how you did this? Find your z-score, and we went like this, and you went like this, and you went like this. So now you're like, yep, I can do that with t now. You're like, I'll just take t and I'll do that. The only thing is, we won't have to do that today, because we got this ready to roll right here, right?
Okay.
But you're gonna do this just like this when we get into chapter 10.
Okay.
Cool? And the only thing is right there is, remember how to use the section 8.1 formula? That's what we use, but we will do this. You go, oh, this will be in section like 10.3. So you're gonna be like this. Oh, in place of this, I'm gonna use this. You're gonna go like that, you're gonna put your X bar here, and you're gonna put that mean there, just like that.
Huh.
Isn't that cool? Let me put a bar over that. But I do wanna point out, everyone, what I wrote on the board now, you don't have to copy, or that won't be necessary till section 10.3. But that's how you get the t-score. And you're like, thanks, Gossett. Which he named the student's t-distribution. Hey, thanks for listening to my boring story. I just think history, I think it's good to know where this stuff comes from, right? So when people go, there's probably stat teachers you don't know where t, why do you just use t? They don't know the real reason. You know the real reason as a student, which is cool. All right, so I got this up here. We've got the t-distribution. Everyone gets a copy. That gets attached to the test, right? That gets attached to the final. So you have no trouble having to figure out a t-score, and we'll do it in the problem. But we're only going to use this t table when we're doing inferential stats about